Let's start the new topic, series resistance. Now, actually, this topic you have studied in the semester 3, but what is the change what you have studied in semester 3 and now the same topic you are studying in semester 4? So, the difference over here that you start your discussion for AC current. So, the connection of resistance in a series that is made up of or that is experiencing AC current. Now, here we will start our analysis, but first of all we see what is the actual series connection. This you have might seen in the law of series and parallel connection. Suppose this is R1 and this is R2. So such kind of arrangement in which we can say the resistance R1 and R2 are connected in a series. So this is the series connection of resistance. Now, if you remember, we have solved one equation, that is differential equation, for LCR circuit. In terms of I, means in terms of current, is given by the equation, and here I am writing the equation. I is equal to Vm cos omega t minus delta. This whole term is divided by the magnitude of z, and that was under root of r square plus omega L minus 1 over omega c whole square. Now, after writing this equation, you have to determine or define all this quantity. Here I is the electric current, Vm is the maximum voltage passing through the circuit, cosine is the function, delta is the phase difference, omega is the frequency of signal or alternating signal, t is the time interval, r resistance, L is the value of inductor, and C is the value of capacitor. Now I am starting my analysis in this way, that I am considering these quantities which means Vm over under root R square plus omega L minus 1 over omega C whole square as Im, means the maximum value of current. So my equation 1 has been now reduced to I is equal to Im cos omega t minus delta. So this is the reduced form of equation 1, and here the value of Im is equal to Vm over under root of R square plus omega L minus 1 over omega C whole square. And now I am substituting or obtaining the value of RMS for this electric current. Therefore, the value of RMS current is IRMS is equal to Im upon under root of 2. Now what is the value of Im? The value of Im is Vm divided by under root of R square plus omega L minus 1 over omega C whole square, and don't forget to divide with this under root 2, and that I am putting in the numerator. Now actually if you remember, the value of voltage of RMS was given in terms of Vm upon root 2. So the numerator is nothing but the value of RMS voltage, and hence we can say that the RMS voltage and RMS current are related by this equation. And now I am writing this equation as number 3. This equation shows that if we go on changing the value of the frequency omega, and this frequency is of voltage, then the value of IRMS will also changing, and hence I can consider at one particular position the value of omega that is equal to the value of omega 0, means the value at 0th position, and hence at this point I can write down omega 0 L is equal to 1 over omega 0 C. And hence in this condition the value of impedance will be minimum, and with the help of the minimum value of impedance, the value of electric current passing through the circuit will be maximum. So see, the physics is related in with how much quantities, and now I can write down the equation 3 in this form, that IRMS is equal to Vrms, and the denominator is nothing but the magnitude of impedance, and so it is equal to Vrms upon mod Z. But here we have assumed that the value of mod Z is minimum. So what does it mean that there is a minimum value of impedance? According to the minimum value of impedance, there is strictly absence of the imaginary parts of impedance, and hence I can write down IRMS is equal to Vrms upon only the real part of impedance, that is the resistive part, and so I can write down this particular quantity as the maximum RMS current, that is equal to IRMS max. And so for a definite angular frequency of voltage, that means omega 0, the value of IRMS will be maximum. And also such kind of arrangement is called the series resonance in LCR AC circuit. Now if you remember, at omega is equal to omega 0, we have obtained one condition that omega 0 L is equal to 1 over omega 0 c. That implies omega 0 square is equal to 1 over LC, and therefore if I want to find out the actual frequency or angular frequency first of all, then I am taking square root on both the sides. Then this will be my angular frequency omega 0, which is equal to 1 upon under root LC. Now if you know the value of omega is related with the simple frequency f, in this way omega 0 is equal to twice pi f0, and so you can find out the actual frequency or natural angular frequency. So f0 will be 1 upon 2 pi under root of LC. And here the f0 is known as the resonant frequency of LCR AC circuit. Here there is a graphical representation of IRMS versus the angular frequency for LCR circuit. Here we have taken the two values of R, R1 and R2, which clearly shows that R1 is less than R2, and such kind of arrangements are called resonance curve. The characteristics of this graph for IRMS versus angular frequency are known as the resonance or the resonant curves. So if you see the resonance curves of R1 and R2, then the resonant curve is sharper for smaller values of R, that you can clearly see from this figure, and the maximum value and root mean square values are also provided at the different frequency. But for the smaller values of resistance, the resonant curve is more sharper. So with this, the series resonance topic is over, and now we will start the Q factor. We have studied about the sharpness of the curve which was arising in the characteristics of the RMS current and the angular frequency of voltage. Means in this particular graph we have observed the sharpness of particular resistance, and the sharpness of such LCR circuit in that resonant curve is measured by quantity, and this quantity is called the Q factor. So Q factor is nothing but a measurement quantity. So how can you measure such sharpness? Whenever you connect the circuit, the maximum power flowing through the circuit is directly proportional to the maximum value of RMS current and its square. So the maximum power is proportional to the square of maximum RMS current. Here maximum word will come. And also when this maximum value becomes again RMS type, that means when it comes to this particular value IRMS upon root 2, then the value of power will be half of its maximum value. So this is the correlation between the power and current actually. And now if you observe the value of IRS max upon under root 2 in the graph which I am giving you again. So here is the graph of IRMS versus angular frequency. Then here the corresponding power is shown, or we can say the corresponding angular frequencies are shown, with omega 1 is having this value and omega 2 is having this value. Now, this omega 1 and omega 2 are vertically at the same point, and so I can say that the bandwidth of this angular frequencies which is given by or which is given between omega 1 and omega 2. So the difference is omega 2 minus omega 1, that is delta omega, is called the half power bandwidth. See, each and every word of this particular definition is important. Why it is half power? Because at this particular frequency range, the value of RMS current is at this point, means IRMS max upon root 2, and at this value of current, the value of power is going to be half, and that's why here the word is used half power, and bandwidth is just showing us the frequency range. And now the Q factor and its mathematical expression is given by, first of all, the denotation of Q factor is given by capital Q. And now you don't confuse between the charge Q and the Q factor. So Q factor is given by the middle of the frequency or the original angular frequency divided by the bandwidth, and that is equal to F0 divided by delta F, because 2 pi will be cancelled from the numerator and denominator. Now from this equation one thing should be clear in your mind, that when the value of Q factor is larger then the sharpness of the curve will be more, and including to this particular topic we have the value of delta omega as R over L. This R over L means resistance over inductance, which is given by the frequency range, and now I am substituting the value of equation number 2 into equation 1. So the Q factor will be omega 0 L over R, and that is the equation number 3. Now we have the value of omega 0, the resonant angular frequency, as 1 over under root L into C. So now substitute the result of omega 0 in equation number 3. We will get Q is equal to L over R under root LC. So the final answer will be 1 over R under root of L by C. So the Q factor can be now determined with this equation by just knowing the components of LCR circuit and their measured values. Now, the Q factor is depending on what? So, it is now very easy to understand from this equation. So, the value of Q factor depends on the measurement of circuit component. And from this value of Q factor, we can now study about how is the tuning of circuit is done and how can you check the selectivity. So from the value of Q, two conditions we can now check: the tuning of circuit and the selectivity of the components of that circuit. Suppose you are using the resonance circuit. Then this circuit is used to select, means to tune a particular frequency out of many frequency. So it is used to select the particular frequency. So can you give me some example of this resonant circuit in your domestical use? So it is very easy. This radio and TV are containing such kind of resonance circuit to select the particular frequency among the given frequencies range. In order to change the particular frequency, we have the arrangement is given to change the condition of L or C. So any change made in L or C will result into the change of frequency, and hence we can tune to the another frequency range. But note that resonance cannot be obtained in RL and RC circuit. So it is only applicable to LC circuit. So we can say this is one of the disadvantage of resonant circuit. So with this, our analysis for the first part is over, and now we will solve some illustrations related to this particular article.